For lab 5, I've chosen to do collisions. Um, so my objectives, I want to show the conservation of momentum. So the change in momentum equals 0. So the final momentum equals the initial momentum. And the total linear momentum is conserved in collisions. And this is only for isolated systems where the net force is 0. So what does it mean for the change in kinetic energy? If the change in kinetic energy is 0, it's an elastic collision. If it's not 0, it's an inelastic collision. And there's such thing as a maximally inelastic collision, which means they stick together after the collision. So the experiment I'm going to be using frictionless carts. I found this video online, and I'm using them because to have the net force equal 0, we must model it without friction. And frictionless carts are something that trying to limit the friction of the system. So first, I modeled collision 1 in Tracker. Um, I modeled it like every other lab, and I was able to get some data from it. I got the initial velocity of the blue cart and the final velocity of the red cart, and you can see that there's a tiny difference in the velocities, and this is going to affect the momentum. So the two periods of movement that I'm saying are the from 0.5 to or from 0 to 0.5 is when the blue cart goes from here to here, and then from 0.5 to 0.934 is from the red cart from here to here. So to model this in GlowScript, I start with just a normal system that's moving, and I put the initial masses of the blue and red cart, the initial positions and velocity, and the initial momentum, and the initial kinetic energy. Then I calculate the total momentum of the system and the total kinetic energy of the system. Then I create a loop for the time period that I said before, t is less than 0.5, and I update the net force vector. Remember, we are assuming it's 0, and we're updating the velocity with the velocity update formula of both, and the position of both with the position update formula. Then I update the momentum of each, and the kinetic energy of each, and the total momentum and total kinetic of the system. Then I plot these on a graph. Then I have the second loop, which is just from 0.5 to 0.934, and it's exactly the same. Then finally at the end, I calculate the total displacement of the blue and the total displacement of the red cart, and then I get the final kinetic energy, and that way I can see the change in kinetic energy. And I also want to see if there is any work done by the surroundings. So if kinetic energy is 0, there's going to be 0 work done by the surroundings. So, and then I calculate the friction that was done on each cart because it's not truly frictionless. So run the code, we see the collision, and we can see that the momentum versus time, it seems like it's changing a lot, but it's a negative 19 to a negative third, so it's barely any change. Um, and for the kinetic energy versus time, it's the exact same thing. It looks like it's a lot of change, but it's really like 0.000685 joules. So from the other calculations, I get the force of the friction on the red and force on blue. I can see that it's almost 0. The outcome, we can say that the collision was elastic and the amount of that change in kinetic energy was so small, we can say it's equal to 0. And for dynamic carts, we can say they're not truly frictionless, but they have a small amount of friction which threw off whether the collision was perfectly elastic. That being said, they're pretty good at limiting friction. So I just want to quickly model a maximally inelastic collision where they stick together. So I do the same thing with Tracker. Then I model it in GlowScript, and I can see that the momentum versus time is almost the same. There's almost no change, and kinetic energy versus time, there's a little bit of change, and the coefficient of friction is almost the same as what we found before. So the outcome, This collision was a maximally inelastic collision. Kinetic energy was lost, and the energy is converted to thermal energy, heating up the carts in a maximally inelastic collision. How do we know this? Because the change in energy equals the work of surroundings plus Q, where Q is the heat lost, and this is where the kinetic energy went since we lost kinetic energy on the left side. Also, since the track is not truly frictionless, this adds to the change in kinetic energy not being zero.